Nak saya cakap dalam BM ke BI ke campur? Hello? Hello?
Hello, Doctor.
Hi, morning. You want me to speak fully in English or mix both also boleh?
Mix.
Mix, eh? Okay. So I guess this is our second time we are meeting everyone from last year. Apa? Etika, right? If I'm not wrong. And saya rasa etika semua dapat A kan masa tu, ada tak yang tak dapat A? Kalau tak dapat A bagi tahu eh. I said everybody got A, which is good. And then for today's class, it will be approximately 1 hour 15, 1 hour 20 minutes because we will be doing combined loading, which is a small topic. So I would like to stress on one thing. So our class is on Tuesday. Oh, sorry. Okay, which is on Tuesday. I cannot write up there. Okay, Tuesday. We start at 8:15 a.m. Is it okay? Or you want to start at 8 a.m.?
Okay.
Okay, 8:15, okay. And then Wednesday is at 12 to 1. And Thursday, what time is the class? 9 to 10, is it? 9 to 10. 9 to 10 a.m. Okay, great. So practically this is our 3 times. So this will be 8:15 to roughly around 9:30 lah. 9:30, 9:45. Okay. And then Wednesday and Thursday. So for this one, we will have 2 quiz. I will have 2 quizzes. One will be on the 23rd of December at 5 to 6 p.m. And one more will be, if I'm not wrong, 6th of January, which is approximately also the same time, 5 to 6 p.m. Usually I will give one question. So it will be a simple question that you need to answer and submit on UKM in UKM Folio. So the questions will be there and so on. And we will not have a final for this paper. Kita akan ada ujian 2. Ujian 2. Nampak Nampak yang saya conteng tu You guys nampak? Okay. Nampak. Alright. Okay, so ujian 2 will be the date we will inform, but it will be on a Thursday, the last week of your lecture, the last week of your semester, of your last class, that will be on a Thursday from 8 to 10 a.m. So that one you will have approximately 4 questions to answer and you have 2 jam to answer. So that will be your ujian lah. So that is practically all about what we need to do for this class. So please bear with me for this last 7 weeks, because I will be with you for the next 7 weeks, sorry. So just nak tanya, how was your midterm? I would say ujian 1. Macam mana? How do you do? You think you did well, or you had any problem, or how? Okay Okay, baguslah. If okay is good. Maksudnya boleh dapat A semua. Steady which is good, which is really good. I hope this can keep up to your expectation. Unfortunately, I cannot be with you. Nak tanya je, hari apa masuk makmal Hello?
Mekanik bahan.
Jumaat.
Ya, mekanik bahan. Pukul berapa? Hari Jumaat pukul berapa?
Ada yang Selasa, ada yang Jumaat.
Oh, okay. Ada Selasa, ada Jumaat. Okay. So, alright. Selasa, Jumaat. So, what time do you enter the lab?
Yang Selasa pukul 2 sampai 4, yang Jumaat tak tahu.
Oh, okay. So, namanya if I'm within the block, then I will come and jumpa you all lah. That's not an issue. Okay, so let's get started with today's class. Today's class we are talking about combined loading. So what is combined loading? As we know, you have learned previously. For example, if I will open one page. Okay. That page. Okay, so when we say about loading, any kind of loading, it can be a stress-based loading or loading-based load onto a component. It will always display a kind of stress, whether it is a bending stress or normal stress. So, for example, in this case, we look at thin wall pressure. In this study, we only focus on thin wall structures, and also we look at components which is being applied loading, various kinds of loading. Say for example, if you have a thin wall structure, something like this, okay, and this wall structure, you have load, you have certain kind of load, and I want to take one piece of here, one component here, so I will always have load onto this, because why? I have a load acting onto the cylinder. It's either thin wall or thick wall, tak kisah. So it will always have a load which is being applied onto the surface of the external surface of the uh, cylinder or pipe or whatever. So we will have two kinds of loading here. One would be horizontal loading, one would be latitudinal loading. So there are two kinds of load acting on a given component. But if we were to have this place as closed and the load is being applied up here, so we have a normal load, which is P over A. That is two things. We will have an additional of P over A, including the horizontal and also the latitudinal stresses. So this one is what I mean by combined loading. Say for example, if I have in this kind of case, if I say this is sigma 1, this is sigma 2. So in this case, I will have sigma 1 will be plus with, say, sigma A, it will be sigma A. All right, and also the other one will be sigma 2 plus minus sigma A, because why? We have to see the difference between the normal load and also the horizontal and latitude loads acting onto the given cylinder. So when a cylinder being applied load, so obviously there will be a combined loading of two loads. One is the horizontal plus minus the normal load, and also latitudinal load plus or minus the horizontal load. But say for example, if I have a shaft, say for example, something like this, round, fixed to a wall. So if I apply a load here, so when I have a load here, so obviously I will automatically have normal load, which is normal, which is on the surface, plus minus with the bending moment. So this is actually caused by two things, because when you have a normal load acting onto the component will obviously have or will incur bending moment onto the given part. So it's either plus or minus the bending moments of the bending stresses of the component. So we have to say, for example, all right. So when we have bending moment and bending stresses, how do I calculate my bending moment and bending stresses? Bending moment, you know how to calculate, but bending stresses will be MC over I. So where C is the from the centroid and I is the second moment of inertia. So that is how we calculate my bending stresses here. Say for example, bending stress. But what happens if I give you a cuboid, something like this? Sorry, please, sorry. If I give you a cuboid, something like this, all right. So, and I give a cross section somewhere here. This is point B, this is point A, for example. Okay, we have two cross section and I apply a load given here. Or I put a load at the end here. Say for example, on here, load over here. So when you just draw this out, you take this out, when you put it here, what do you see? Well, is there a one tension, two compression, and three tension and compression? What do you see at the given points? Say for example, if I apply load here, if I apply a load here, what do I see on point A and point B? What do I see? Anyone? What do I see in point B? For example, if I have a point here, I have point here. So point B, what do I have? Do I have compression, tension, or compression and tension? Which one? Which one do I have?
Both.
In point B, siapa tu? Izan ni?
Yeah.
Okay. At point B, we will have compression because why? When the load is being applied, this component will automatically be something like this. So you have compression here. So you will have the moving of the stresses from the original condition going down. What about point A? Point A will always, okay, you remember the first law, meaning point A will always react in the opposite direction, meaning it will go up. How much it will go up? It will be based on this part. So how much it goes down? So it will be, in point A, we will have tension because it's going up. Point B, we will have compression. But in point A, we must never forget there is also compression. Why? Because the entire component, the entire structure is or component is going down, but it is being resisted by a tension force to actually maintain its integrity, so that the tension will always be there, but it must be a compression negative plus tension. But then still remember, we will always have this one, we will always have plus minus P over A, which is my normal stress. Even this one, we will even have P over A, my normal stress. Because why? The stress is acting onto the surface or onto the surface of the given component. So this is what it means by combined loading, meaning we combine one component under a given load, but you can see two occurrence, meaning you can see normal stresses and also bending stresses. If it is rotation, if it is a rotation shaft, you apply load and it's rotating. So how about that? That you will see that you will see the normal load POA plus T over J. This you have to see because it is near similar to your second moment bending moment, but this is my rotational speed based on the torque and also based on the fourth moment of polar. So this is what happens when you have a rotational shaft. So this is what you mean by combined loading. Say for example, if you have a component like this component, understood, it is not rotating because why? It is only having bending moment because it will bend this way. And if I apply load on this surface, can it have a load this way? Yes. Why? Because I will always see the moment. I need to calculate moment. Moment is force times distance. I need to know. So that is how we actually see combined loading. Okay. So under combined loading, there are a lot of things to see. Say for example, we can see certain issues such as what you call shear stress, average shear stress. When we say the average shear stress, we can see the shear stress as the average would be, sorry, okay, T over 30 over AM. So this is how we see our average stress. Average stress is the mean area enclosed on the within the boundary of the center line. So what is the center line? We can see how far from the center line, if it's in the centroid or not. Okay, so now we go to further a bit. Then we look at thin wall pressure vessel. When we talk about thin wall pressure vessel, we understand when load is being applied onto the pressure vessel. Just imagine if I have a shaft like this. So just ignore the bobohan dalam. So if I have a shaft like this, where do you think the load is being applied or the pressure is being applied? Is it latitudinal and horizontal, or just latitudinal, or just horizontal? Which one? If it's just sitting static like this, so where do you consider in horizontal or latitudinal? Tak ada orang jawab, saya panggil nama. Aina Madria. So Aina, where do you see the loads? Where do you see? You see horizontal, latitudinal, or both?
Both.
Both, yes, that's true. Because why? You will obviously have gravitational load, which is acting onto the wall of your cylinder inside here. Say, for example, that's why you can see the buah inside here is being on a stable position. It is not sinking, neither is it floating on top. Okay, so that is when we have pressure. So when we cut that what do you call? If I see both, I will have latitudinal and horizontal stress, even like a pressure vessel. For example, a spherical pressure vessel, or like for example a bola lah. A bola also will have latitudinal and horizontal. Why? It needs to have both stresses for it to have an equilibrium to maintain its structure. So now, have you ever wondered why you have a Coca-Cola can? All right, you have a Coca-Cola can, you open, you drink the water, and then you put hot water. What will happen if you put hot water inside the Coca-Cola can? You dah minum Coca-Cola, you dah habis Coca-Cola tu, or Pepsi or whatever, you put hot water into the can. So what will happen? Badrul Akmal. Ada Badrul? So what will happen if you put hot water inside? Mana Badrul ni? Badrul? Oh, Badrul. Anyone? What will happen to the can, for example?
Expansion.
Sorry?
Expansion.
Okay. So when will that? Because why? Why? Because of the latitudinal stress or horizontal stress is either either greater than the horizontal stress. So therefore, it will start to keme and so on. So therefore, you will either have this or this. So this is how we analyze the structure of the thin cylinder or also pressure vessel, for example. Okay. So when we talk about thin cylinder, we will have, for example, sigma 1, which is PR over T, and sigma 2 would be PR over 2T. Why? When we talk about sigma 1, it is always acting on the surface, onto the surface. All right, that is the sigma 1. So whereas sigma 2 will be, if you look at the cylinder, it will be acting here onto the circumference of the cylinder. So therefore, we will always use sigma 1 to represent PR over T and sigma 2 equals to PR over 2T, double the thickness. All right, so this is how we see our combined loading. So if we have a thin wall structure, say for example, latitudinal stress, we will always calculate as PR over 2. And if it's a thick wall structure, we will always use this one. So can anyone tell me how do I differentiate thin and thick wall structure? How do I do that? Anyone?
Ratio between RO and RI.
Okay, RO over RI. So what is the ratio supposed to be? And then comes out the second question. How do I know what is the ratio? First we know, okay, we know. You said what do you call? The thing is thin wall or thick wall, we say based on the ratio. But how do I know? Anyone? How do I know? How do I know? How do I know? Anyone? So this one, I want you to tell me in our next class on Wednesday, because there is a ratio of RO over RI, which is supposed to be more than 0.5. But then please let me know betul ke tak RO tu. Alright, so this is how we calculate for thick wall and also for thick wall internal pressure and also external pressure. When we talk about thin wall section, we are only concentrating on the external pressure. We don't consider the internal pressure. Why I don't consider the internal pressure? Because for thick wall, the internal will also be the same as the external. So therefore, if anyone asks you, okay, can you calculate for thin wall for internal? Yes, I can calculate because it's the same. How about the external? Yes, it is also the same. So I can use this. But whereas for thick wall, internal pressure, we have two. We have to use this equation. Sorry, that's not that nampak sangat. Okay, we have to use this. So there are two, right? So when we look at this, okay. So when we look at this, average shear stress, okay. Then with this, I give you a simple example. Okay, let me just add a page. Okay. Okay. Add page. Okay, say for example, if I have a tank, cylinder tank, example. If I have a cylinder tank, all right, I know it's a thin cylinder. One thin cylinder. Or thin cylinder pressure vessel subjected to internal pressure. It has pressure internal of, for example, 600 kilopascal, and then diameter of the tank is 500 mm. Okay, and I know the thickness of the diameter would be 6 mm. There are two. Okay, I've got two. One is the pressure internal, and I know the diameter is this one, and also the thickness. So if in order for me to, I need to know, one, I need to determine the stress acting on the given point, say for example, this is point A. On point A and 2, I need to draw the volume of element at this point. Element at point A, for example. I've got 2. So in order for me to determine the stress, I know it is a thin cylinder scenario. So fine, if I know it's a thin cylinder scenario, sorry, 600. Okay, if I know it's a thin cylinder scenario, then it's no problem. I can know my stresses will be sigma 1 would always be what? PR over T, and sigma 2 would be PR over 2T. So I know this. But what happens now? So I know I will replace my values. So pressure being applied, this one is 0.6 because we changed to megapascal. Radius we changed to mm. So it is berapa? 550 divided by 2 is 500. 500 divided by 2 is 0.25 divided by how many? Sorry, 600. Sorry, 600. This one is divided by thickness. Thickness is 0.06. So I will get approximately berapa? So whereas for this will be also same. Sigma 2, 600 multiplied by 0.25 divided by 0.12, because why? I multiply my thickness double. So when I have this, so what would my sigma 1 and sigma 2 be? Anyone can tell me, please? I tak ada calculator, I tak boleh tekan-tekan. So what's your, what would the answer be? Answer should be in megapascal, yeah? So what would that be? Mio Syami? Ada? Sigma 1 berapa?
Sigma 1 is 2500.
2500, okay. Megapascal or 2500 kilopascal? Tadi siapa jawab ya? Sorry tak tangkap nama. Mio jawab ke tadi?
No, doctor, it's me.
Oh, Irfan. Okay. Sorry. So 2500 megapascal or 2500 kilopascal?
Just 2500.
Because here is kilopascal. So you be kilopascal. So end of the day, so it's 2.5 MPa lah. Okay. So how about sigma 2?
1.25.
1.25 megapascal, is it?
Yeah.
All right, great. So then if I ask you to draw the element, so how do I draw? Simple, yeah. So I have this. So which will be sigma 1, which will be sigma 2? Obviously, this will be sigma 1, which is approximately 2.5 megapascal. Sigma 2 would be this one, because it is 2.5 megapascal. Okay, so we have that. So this is a very simple example, but the same example, I give back the same. So if I can just draw back the same cylinder. Now we know it is a thick cylinder. All right, we know it is a thick cylinder. I say one thick cylinder. So I say same thing. Pressure being applied is 600 kilopascal. And then diameter outer is 500 mm. diameter internal is 250 mm. Same thing. So now we know it is another case of thick cylinder. Another case of thick is a case of thick cylinder. Does the opposite, but we know this thing. So can I say, for example, where was the equation earlier? Can I calculate the thickness of this one? Can I calculate the latitudinal stress? I want to know latitudinal stress. Is it possible? Yes, it is possible. Why? Because I still just go back and look at the equation. What was the equation earlier? Okay. Minus over okay, so it is based on this equation. I want to see the internal and also external pressure. So if I want to see the internal pressure, I use this equation. Simple, directly. If I want to know the external pressure, I use this equation. Same. So this is a combination, meaning if I want to know internal, so it will be where we go back to the equation, Rho minus Ri. If I want to know external, it will be negative okay, great. So can someone please calculate for me the internal and external pressures, please? So we know this one is diameter, this one radius will be 250 lah. Radius will be 125. So someone, can you calculate the for internal, for external, outer? Someone, please, can I give you a few minutes?
300.
Sorry?
300 kilopascal.
600.
300.
300, great. Kilopascal, eh?
Yeah.
So you'll be 0.3 megapascal lah. Okay, great. How about the external? How about the second one? After this, there is one more example for thin cylinder. Then we go to combined stresses.
Negative 600.
Negative
0.6 megapascal.
megapascal. Always remember, please keep your answer in megapascal. Don't keep in kilopascal. Right, so this is how we calculate for internal pressure and also external pressure for a thick cylinder. Quite simple, kan? So, okay, what about if I have one more question? Say if I have a gas stone, for example, a gas stone, all right. Point, say for example here is point A, and I know 200 kilonewton is being applied. I know this cylinder, we assume this is a thin wall cylinder, yeah, thin wall. Radius to be 600 mm. Okay, thickness will be say 10 mm. Okay, so what I want to do is This is quite simple, just one only. Determine the state of stress at point A, for example. Okay, I've got this. Now I want to determine the state of stress at point A. Okay, so when we look at point A, we will obviously know this is a thin cylinder issue. I will always have two things, sigma 1 PR over T and sigma 2 PR over 2T. Okay, so I know this. Okay, so I want to calculate the state, the state of stress at point A. How do I determine state of stress in point A? Say for example, if this one, I cut this thing out. So if I cut this thing out, I have something like this. Something like this, betul? And then I have the bottom part here lah, which is at the bottom already, which is at the bottom here. Okay, something like this. So I know I apply 200 kilonewton here. All right, I know I apply 200 kilonewton here, and I know I have stresses here. Stress 1, stress 2. Stress 1 is what stress? Stress 1 is always
longitudinal.
Yes, stress 2 is horizontal. So horizontal, which is coming down. So that means you will have stress 2. You will automatically have another load which is acting in the opposite direction. Why? To maintain the equilibrium or the stability of the given pressure tank. So with that, you know you will have plus minus P over A. Because why? Now we assume going down load is positive, acting opposite direction to be negative. So therefore you will have, for the first state stress is okay, because why? It is acting here on the hoop of the cylinder, so there's no issue. You will not have any normal stress. But when you talk about this one, you will obviously have normal stress, because why? You need to maintain the stability or the integrity of the given structure. Therefore you will have a normal stress included into this given cylinder. So let's calculate for stress number 1. Stress number 1 would be pressure. How much is that? 200 kilopascal. Radius is around 0.6 divided by 0.01. So you will have sigma 1 as your answer. Berapa ya? And sigma 2 you will have 200 times 0.6, 0.01 plus minus P. P would be apa? P would be 200 also. A would be the area lah. Area will be pi r. R will be 0.6 squared. Okay. So for the first one, you akan dapat berapa? How many megapascal?
12 megapascal.
12 megapascal. Okay. So how about the second one? How about the second one? Second one, we know this is 2 plus, sorry. So this would be 6 plus, this one positive, negative. That one we have to see our vector. If we say our loading is positive towards down, so therefore the normal load to maintain the stability or the integrity of the component will be acting onto the positive onto the negative region. So therefore it will be minus whatever 200 over the one. So you will get berapa megapascal? Berapa megapascal? How many megapascal? Anyone? Najwa ke? Najwa Izati?
23.
23. Negative, positive?
Positive.
How come positive? Because it's a negative. Minus.
Hmm.
We use.
Bukan minus.
Yep. 6 minus. Ini berapa? 200 over 2 times 0.6
Oh,
square.
sorry.
Berapa tu? So how much do you get? Anyone? Somebody?
Negative 159.
Negative 159. Okay. Okay. So now, okay, that is one example. When I go to one, there's a third example. I won't show. That one is okay. But one thing, we're going back up again. Where were we? Pressure vessel. Okay. Are we going? How do I differentiate this thing? What I mentioned earlier was this one. Regarding your pressure vessel, how do I differentiate thick wall and thin wall? Is it the ratio of internal over external, or we can say this one? We will always see the rule of thumb is this. Rule of thumb to determine whether it is a thin wall or thick wall is the radius over the thickness of the wall. So if the radius is bigger than the thickness of the wall, hence it will be a thick wall structure. All right. If the thickness is the other way around, so therefore it is a thin wall structure. So this is how we explain in terms of knowing a cylinder, is it a thick wall or a thin wall structure. Okay, so I've given 3 examples. This is a very classical example of combined loading. All right, so now we look at combined loading. Combined loading, we have average shear stress, which we understand where average shear stress will occur onto the surface of the component which is being applied the given load. So the average shear stress acting over the thickness of a tube, for example, and T will be the resultant internal torque at the given section. Say for example, if this is a section, so therefore there will be a given torque because it is under rotational, and also the thickness of the tube, where the average is determined based on the mean area enclosed within the center line of the tube's thickness. So that is one. So when we see state of combined, so when we look at the first example like this, for example, we have this, and I know this is my given point like just now, point A. So if I'm given a load perpendicular to the normal surface, so I will have a bending moment occurring. So when I calculate the bending, I can always use bending stresses will be MC over I. I will be based on the second moment of inertia. But if it is a rotational basis, I will use TC over J, where T is the top, over C is the center of the point, and also J is the fourth moment of polar. Right, just give me a second. All right, so that is how I determine the state of stresses based on the combined loading. But what happens if I have a state of this one? Oh shit, sorry. Okay, if I have something like this, and I have X, Y, Z, Y, X. Okay, so how many kind of moments do I have here? Do I have MZ, MX, MY? Am I right? I will have all these three. Or no? Or do I only have MZ if I have loads on three directions? How many bending moments would I have? If I have three loads, how many bending moments would I have? Class? Azima Nazri?
Maybe 3, I guess.
Yes, 3. Because when you have 3 loads, you will obviously have 3 bending moments. So if I were to put my bending moment here, this is my MZ, okay, XZ, MZ, MX, sorry, and MY. So how will the moment be? Will it be rotating clockwise or anti-clockwise? So with that, how do I know? Clockwise or anti-clockwise? Bopinda Singh. How do I know whether it's clockwise or anti-clockwise? The bending moment will be clockwise or anti-clockwise? Bhupinder Singh? For MZ. Bhupinder Singh in the class? No?
Yes, doctor.
So now we know MZ. Okay, so MZ will be what? Rotating clockwise or anti-clockwise?
Clockwise.
How do you determine it's rotating clockwise?
I'm not sure.
Okay, simple. You see the load. I show everyone. You see this pencil, right? This pencil is assuming to be the load in the up direction. All right. Okay. Before that, I try one more. Douglas Chong in the class.
Yes, doctor.
Okay, Douglas. So for MZ, will it be clockwise or anti-clockwise?
Anti-clockwise.
Why?
Because the right hand grip.
Right hand grip. So we follow the right hand grip. Assuming this is a load being applied on top. I hope you can see the pencil. So when we have this, you see your fingers. Where your fingers going in? It's going in. So where's your fingers going? It's going this way. So this will be your positive direction. How about MX? MX is going out this way. You see it is rotating inside. So meaning it is rotating this way. And MX, it is this way. So meaning it is rotating this way. So this is what we have. We have MX, M, all three. All right. So this is actually important when you calculate your bending stresses. So with bending moments, you will have 3 bending stresses in the MZ, MX, and MY condition. So meaning you know your shaft, this one can, if you have Z load, meaning it will rotate something like this. if you have external loads, it will, oh shit, sorry. If it's external loads, you will have this one rotating this way. And finally, if you have something acting this way, you will have this way. So you will have three directions. So X, Y, and Z direction, right? Okay. Please pay attention a lot because this one might come out in your ujian 2, one of the question lah. So how to calculate based on the given problem. All right. So when we look at combined loading, we have forces perpendicular, F over A, some say P over A. For me, I prefer to use P over A. Some would use F over A, same thing. Bending will be MC over I, whereas for the shear stress for rotating will be shear stress will be VQ over IT. So Q is actually calculated with A prime, Y prime. So that one we have to know A prime and Y prime. And then torsion, for normal stress, there will never be torsion. For rotating shaft, you will have a torsion based on the given torque and also second moment of fourth moment of polar. So when pressure vessel is the same thing. Pressure vessel is practically normal stress. Okay, so combined loading. So when we talk about thin wall, refers to a vessel having an inner radius diameter ratio of 10 or more. So like what I mentioned, we have R over T. So then only we know it is a thin wall or thick wall structure as mentioned earlier. Okay. So with thick wall, the assumption taken is that the thickness of the pressure vessel is uniform and constant. It will never be different. If it is different, then it's we cannot calculate the thing. Say for example, before we go to this is thick wall, same thing I've done, we've covered. Combined thick wall, we've done the example. Okay, combined thick wall, yes, I've done the example. Cylinder, yes, and radius for cylinder. Okay, this is example we have done. I've covered. This is actually in your textbook. Okay, so I go here straight directly. I will go to slide 20. What's this? 23, and I add one page. So now when we look at a cylinder, so we know a pipe. Okay, a pipe is been fixed. And this pipe is to transport, say for example, oil. Oil coming in. Okay, we know the diameter is 4 mm. The thickness is 0.2 mm. 0.2 mm, for example. And it carries oil or water, whatever, load of say 0.6 megapascal. Okay, now I want to determine the state of stress in the walls of the pipe. Okay, so now I know this is a pipeline coming from refinery oil pipe, but I know it has a thickness 0.2, diameter of this one. So what I need to do is I need to know how to solve. We know how to calculate. We know it's either using PR over T or PR over 2T, because why? It is occurring along the entire part, and I'm not concentrating on for example, a given on a given point, not even point A. No, it is not given point for the entire pipe. So when we talk for the entire pipe, we know there will be either this or this. But goes back to the question. Thick or thin? So how do I solve this? Thick or thin?
Thin.
Why do you say thin?
Because dia ngam-ngam 10 ratio.
Ngam-ngam eh? Ngam-ngam berapa?
Ratio
Pak?
dia 10.
Ratio dia 10. Okay, ngam-ngam lah. So, okay. So, when we say ratio is equals to 10, approximately 10 lah kan. So, we say we use apa? Tin kan. So, when I say tin, I can always fall back on this or this. Okay. Now, the question is, which one should I use? Should I use P1, P2, or P1 only, or P2 only? Mana satu? We have to look at the pipe itself. If the pipe has open ends, sini buka, therefore we do not need to calculate this. Alright, we do not need to calculate that. Please bear in mind, if a pipe that has open ends, both side, kiri kanan both ends, so that means we can consider there is less or minimal load being applied onto the stress for the second part, the second stress point. So therefore, we only calculate PR over T. Alright? Boleh Okay, so what do I get if I calculate PR over T? 3. 0.6 times with radius berapa Radius, okay.
2.
0.02
Radius 2. Oh,
Kenapa?
dalam meter 0.02. Yeah.
Okay, thickness, lagi kecil lebih kurang So what do you get? You get one number lah. You calculate yourself. You can see. But now the same question, I say this part is being closed. In this part ada. This is to store. Exact same question to store oil or water. And this part is closed lah. Close. Tutup. Sini air masuk. Or oil masuk. So what do I do? Do I still calculate sigma 1, sigma 2, or sigma 1 only, sigma 2 only? Which one do I calculate? The earlier one I said because it's open, so therefore you only calculate sigma 1. But now in this question, I say it is closed. One side dah tutup. Sini dah tutup. So how do I calculate? Both, yes. We calculate this one and we calculate this one. This one does not apply because why? The loads will be acting onto the walls in horizontal and latitude, or some people say hoop stress or whatever. Same thing. All right. So okay, that is how it is there. Okay. Now we go to see state of stresses combined for superposition. Superposition meaning we have stresses acting in the x-axis. Sorry, not x-axis. We have stresses, both stresses, meaning load, normal, and also bending. So then we will have a case where we call it as superposition. If it's rotating, you will have load, you will have normal load and also rotational load. Macam tadi, that is considered as superposition, combination of two or more stresses acting on a given state stress or a given point. So we assume a linear relationship of the load and the stresses, assuming that geometry of the member should not undergo significant changes when being applied. So for example, this is how the calculations are, but I'll go straight directly to an example. So this one, okay, this one you guys can see in the example. I won't give this example, I'll give another one. Page. Okay, so the rest I will send to you guys as soon as the class is over lah. Alright, as soon as the class is over. You guys nak lecture note yang diconteng ke ataupun lecture note yang tak conteng, yang kemas-kemas tu?
Diconteng.
Yang ni lah.
Cantik.
Nak yang ni lah, in other words.
Yeah, yeah.
Okay.
Yes.
Alright. So I will give you two. One the cantik punya, sebab cantik punya dia punya equation you nampak. Yang tak cantik tu equation dia lari sikit. So not to say lari lah. In other words, you see box, you don't see the equation much. So I will give you both. Alright. Okay. Say for example, if I have a cube. Okay. Okay. Okay, if I have this, and I know there is this center line. Di tengah, titik tengah. Okay, and I have a load being applied here. Okay, I have load at this point, 300 Newton. I have the load is 300 Newton here, or say for example 300 kilonewton. Right, excuse me. I tahu jarak ni, say 50 mm. I tahu jarak ni 50 mm. And I tahu this jarak is 150 mm. 150 mm. Okay, all right, Chun, we have this. So now what happens is ni berkurang. So I have this point acting here, which is here at the front sector. Oh, tak apa, allocate balik, sorry. My mistake. Figure tak, betul, sorry. Okay, so drawback, sorry. Okay, if I have something like this, all right, much better, correct. Okay, if I have something like this, sama juga, if I have the load 300 kilonewton, and I know jarak dia tengah sini is 50 mm. This is 150 mm. 150 mm. All right, so I know this is one point in the center, or maybe not center, up to me, up to the thing. So this is point C. This is point B. Okay, we know force of 300 kilonewton is being applied to the edge of the point. Say point A. Of point A. Okay, we know point A at the end there. So I want you to determine one, state stresses, stress at point B and C, both given points. So this one you have to pay attention also, not everything everything you have to pay attention. Okay, and then second, the distance x based on the resultant force, okay, or the stress, certain force or stress distribution. Okay, so we have this. Okay, great. This is clear. Apa ni? Okay. Okay, we have this. All right, so we have this thing in. So how do I solve this? We know this. Okay, so how do I solve this? What am I trying to find? What am I trying to find? What am I trying to find? I'm trying to find the stresses at point C and point B. Betul. But I know what's happening at point A. So how do I do that now? When I do this, okay, I tambah lagi page lah. That's the bottom is example 150. Page. Okay, you can see the second example. So when I do this, I cut this part out. So I know the first section, this part. All right, I know this section. Say for example. Okay, I know here is C. I know here is B. Okay, I know this is your. There will be something like this. Betul? So whatever happens here, say for example, whatever happens on the point A, okay, will be a resultant from the centroid of the cuboid. It will occur in the centroid of the cuboid. So when we have centroid of cuboid, so what will we have? If we have centroid cuboid, this point C, point B, when load is being applied here, 300 kilonewtons, what will happen to C? Will C move down or move up? Will it have compression or tension? Which one?
Compression.
Compression. Obviously, it will start to have compression. Good. So what about B? B will be what? B will be the opposite or resultant load acting on the opposite direction so that it will maintain its takkan dia duduk turun macam ni, tak ada, because wire is being applied at the end. If it's being applied at the end, this will be apa? Tension or compression? So obviously when you have compression here, the opposite direction will be tension or compression?
Tension.
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 Okay, so okay, we know 300 here. Okay, 300 kilonewton. Do you know any, when you have here, what will happen in the middle here? You will always have bending moment. Sebab apa? When you apply load here, here will hold, sorry, here will hold. Obviously, there will be some kind of apa ni? Okay, so you will have some kind of bending moment occurring at the bottom. So you will have a bending moment occurring in the center of the apa benda? Of the cuboid. So what is the bending moment here? The bending moment is calculated as M equals to, ialah M equals to bending moment will be berapa bending moment dia? 300 Newton, kilonewton multiply with berapa? Distance, right? The distance will be 0.15 meter. So you will have approximately bending moment of 45 kilonewton meter. Okay, you following me? Hello? Okay, great.
Yes.
Yeah, okay, great. So you have this. So you have that bending moment. So there are two components in this to solve this one. We have two components. One is my normal force. Normal force is calculated as P over A. What is P? P is the pressure load being applied, which is 300 kilonewton. A would be the area of the cuboid, which is earlier saya dah bagi berapa? 150, 3.3 times 0.1. So akan dapat berapa? meter square. So dapat berapa? 300 divided by 0.03, 10,000. Betul eh? How much?
Betul.
10,000 kilo, 10,000 will be 10 megapascal lah. Betul? Alright, good. So what else? Is there any other load being applied? Yes, when you have bending, will you have a bending stress? Obviously, you will have bending stress because why? When your component is being this one, so obviously there is bending stress in the center. Dia akan to bend the component because of the load being applied. So when there is a bending moment, obviously there will be bending stresses. Bending stresses, stress caused by who? By who? By the load lah. Caused by the load. So sigma m max, I would say bending maximum, would be mc over I. What is m? M already calculated. 45 kilonewton meter. What is c? C is the center of the from the centroid, so will be 0.15 mm meter. I is apa benda I? Second moment kan? Second moment untuk cuboid berapa? 1/12. I for this will be 1/12 BD cube. So B will be 0.1. D will be 0.3 cube. So dapat berapa ni? Dapat berapa? Dapat berapa? So I know my bending stresses are this one, whatever the number is lah. Can someone please calculate for me?
.7 megapascal.
Betul ke 2.7? Betul ke 2.7?
30K.
30 megapascal lah. Okay. 30 megapascal. Okay, great. Because we use megapascal for to calculate, so settle 30 megapascal. Okay, now we know this. Add lagi page. Kita tambah page lagi. Okay. So with this, we know this is your cuboid just now. Your structure which I cut out. We know there are loads acting here. All right, acting in this direction. Why? Because it is the opposite or resultant loads in the opposite direction. This is A, my normal stress. Whereas B would be my bending stress. Where was I? Okay, draw back benda ni. So kat mana titik tengah tadi? Titik tengah kat sini kan? So when I know I have bending stresses, on a general term, in the center, in the center, it's supposed to be something like this. Something like this in the center. So we know the load is acting this way. Great, we know the load is acting this way. So kalau ikutkan, it's supposed to be load also acting in this direction, which is equivalent. Tapi sekarang we have to go back to the basic understanding of physics. This is superposition already. Must go back to the basics of physics or mechanics, whereby if you have load acting here, automatically this will be an opposite direction. Why? For first law of Newton, opposite and equal direction. So same thing. So with this, how do I calculate superposition for point? This is point A. Where point tadi? B and C. Okay. B and C. B and C. How do I calculate point B and point C? Very simple. I know for point B, it is normal stress plus minus apa? Bending stress. Shear stress or bending stress. Point C is also normal stress plus minus bending stress. Betul ke tak? Do you agree with me on this? Point B is normal stress plus minus bending stress. Point C is also the same thing. This is point B lah tadi. Okay, so this is happening. So, but at point B, we notice normal stress, now we know the load is acting bottom, which is we take as positive. So the opposite direction for point B, so we calculate for point B first. So the opposite direction would be negative. Normal stress would automatically be negative 10 megapascal plus the bending stress. Bending stress berapa tadi? 30. You will have 20 megapascal. How about point C? Point C, we know, obviously it is acting, the normal stress is obviously in the opposite direction, which is negative 10 megapascal, plus or minus? Minus lah sebab because it is coming down. So, coming down, which is your bending stresses, which is 30 megapascal. So you will have 40 megapascal. So in other words, your stresses have already transformed from this state okay, something like this. Okay, this is 40 megapascal and this is 20 megapascal. So you guys following me still? Yes? No?
Yes.
Yes.
Okay, good. So now you're clear on this. But now go back to the second question. Second question tanya apa? Second question dia tanya, mana soalan tadi? The distance of x based on the resultant forces. So how do I know? This is no more. In order for it to be, was your original center point. In order for it to be in the stability or stable position, this point has already shifted so that it will be maintaining its stability. So how do I calculate that stability? So it is quite simple because why? We know that the entire distance is x. And from x to, say, for example, how many? 300 megapascal. Okay, because why? 300 mm. So how do I get 300 mm? The earlier this structure will be, if this point, this will be, this is 300. So this will be 3, we do not know the distance. This will be 300 minus x. This also will be 300 minus x for this. If this is x, this will be 300 minus x. So that is quite simple. So how do I calculate for this now? I want to know the resultant stress distribution. I can do simple interpolation. The 20, if it's fixed here, 20 to for the distance of x, must equal to 40 over of 300 minus x, or this distance of x. So we can interpolate that to determine my value of x. Dapat dalam x to be around berapa? 100 mm, roughly lah. So that is my new center point for it to be in a stable condition. So this thing is important. Why? Because you need to understand the concept of what do you call? concept of apa benda kita panggil tadi, superposition, and also understand how is superposition influencing the stability or also the centroids of the loads based on its point loading. So ya, ni ada example kat sini. Ini I will give the slide tomorrow lah, not today, tomorrow. These are all examples what we did just now. Some examples here. So this one I will share it tomorrow with all of you. So I will see you all tomorrow. Ada apa soalan sebelum kita berakhir hari ni? Anyone? Don't feel shy. Please, you can ask me anything. If you malu-malu nak tanya, I don't know whether you still keep my number ke tak. Just providing. So you can just call me lah kalau apa-apa nak jumpa, nak tanya about this thing you don't understand. No problem. Just text me and I try to assist as much as possible. Alright. So ada apa-apa sebelum kita tamat untuk hari ni? Hello? Oh, tak ada, bro. Tak ada. Okay. Kalau tak ada, kita jumpa esok untuk 3D problem.
Doktor?
Yes, ma'am. Yes, sir.
Saya nak tanya pasal jadual yang tadi doktor terangkan jadual tadi tu kan?
Jadual mana?
So, kita Tuesday and Thursday untuk set 4 kan?
Saya ikut jadual yang biasa je. Oh, yang atas tadi tu
Yang atas tadi.
Kejap ini ikut jadual yang kelas biasa kan?
Kelas biasa tapi yang kalau set tak silap saya set 3 hari Rabu, set 4 hari Thursday.
Okay, no problem. You just follow the given, Wednesday, if you patut masuk Wednesday, you masuk Wednesday. If you patut masuk Thursday, you masuk Thursday lah.
Okay. Thank you, doktor.
Tapi bagi saya, no issue if saya katakan Rabu you tak boleh datang sebab Rabu and Thursday is more tutorial. So kalau Rabu you kata you tak boleh datang, you join on Thursday lah, tapi maklum kat saya.
Okay, doktor.
Alright, so vice versa lah, Thursday punya group pun kalau katakan Thursday dia tak boleh datang, dia nak join Rabu, just let me know. WhatsApp saya saja. Alright?
Thank you, doktor.
Alright, thanks. So kalau tak ada apa, no problem, just I will see you all bila? I will see you all esok lah pukul 12 sampai 1. So sebelum kita berakhir, mana? Stop recording lah, habis lah. Alright, thank you.